Good morning, respected teachers and dear friends. I'm Lavish Verma, and I welcome you all to my presentation on visualization of 2D and 3D scalar fields. This topic lies at the intersection of mathematics, computer science, and real world applications, particularly in fields like medicine, engineering, and scientific research. Let's begin by understanding the fundamentals. To begin with, what exactly is a scalar field? A scalar field is a mathematical function that assigns a single real number to each point in space. We can represent it like this: fxyz r, meaning that every point in 3D space maps to one real value. Scalar fields describe many real-world phenomena like temperature variations in a room, gravitational potential around a planet, or pressure in a fluid. These fields can be discrete, such as in a grid or point cloud, or continuous, such as when expressed by a function or surface mesh. This flexibility makes scalar fields useful for modeling various natural and engineered systems. Let's explore the two types of scalar fields based on dimensionality. A 2D scalar field represents values across a flat plane. A common example is a weather map that shows temperature across regions. A 3D scalar field extends this idea into three dimensions. Think of MRI scans showing internal tissue densities. By using 2D or 3D scalar fields, we can better understand how physical quantities vary in space, whether it's tracking airflow over an airplane or detecting tumors in the human body. Why is visualizing scalar fields important? Enhanced understanding. Visualization makes it easier to detect patterns or anomalies that are otherwise hidden in raw numbers. Data analysis. Scientists use these techniques to analyze complex systems like fluid flow, heat distribution, or even climate behavior. Decision making, visualizations help professionals, engineers, doctors, researchers make more informed and accurate decisions. Whether it's saving lives or optimizing designs, scalar field visualization plays a vital role. Let's move into visualization techniques. The most basic form in 2D is color mapping. Here's how it works. Each scalar value is assigned a color, commonly using schemes like grayscale, rainbow, or perceptually uniform palettes. For example, red might show high temperatures, while blue shows lower values. It's important to choose colorblind friendly palettes for accessibility and to adjust the scale to highlight important data ranges. Let's look at a practical example. Temperature maps often use red for hot areas and blue for cold. This visual distinction helps users quickly identify trends or anomalies. In medicine, 2D scalar visualization is used in CT and MRI scans for diagnostic purposes. Carefully selecting colors improves not only the look of a visualization but also its clarity and accessibility. Two more techniques in 2D visualization are contour lines and height fields. Contour lines connect points of equal scalar value, like elevation lines on a map. Algorithms such as marching squares are used to generate these efficiently. Height fields represent scalar values as height, turning a 2D plot into a 3D surface, like a terrain model. Adding shading and textures can enhance depth and realism. These methods make complex data easier to interpret visually. In 3D, one common technique is the use of isosurfaces. An isosurface connects all points that share the same scalar value, like a 3D contour. This is widely used in medical imaging to visualize bones or organs, and scientific simulations to show density or temperature layers. It helps extract meaningful shapes from within complex 3D volumes. Another powerful method is volume rendering, which displays the entire 3D scalar field directly. It uses ray casting, where rays pass through the data and accumulate color and transparency to form an image. This allows us to see inside the data without extracting a surface. Transfer functions play a key role here, mapping scalar values to colors and opacities to highlight features like bones or tissues. This is particularly useful in medical imaging and scientific exploration. Cutting planes provide a way to explore scalar fields interactively. They act like virtual slices through a 3D object. You can apply color maps or contours on these slices for easier analysis. Users can move and rotate the cutting plane to investigate different internal layers, making it an ideal tool in medical and engineering contexts where precision is key. Scalar field visualization has wide-reaching applications: medical imaging, diagnosing diseases and planning treatments, scientific research, studying phenomena like climate patterns or fluid dynamics, engineering, stress and strain analysis in mechanical systems, geoscience, mapping geological layers, oil fields, or earthquake zones. In each case, visualization turns raw data into actionable insights. Let's look at some of the most common tools used for scalar field visualization. MATLAB, excellent for mathematical analysis and plotting. ParaView, an open source software for handling large-scale 3D data. VTK, Visualization Toolkit, a powerful library for 3D graphics and image processing. Python libraries like Matplotlib, Mayavi, and Plotly support 2D and 3D visualizations with interactivity. Each tool offers unique strengths depending on the application. To summarize, scalar field visualization helps us understand how data values change across space. In 2D, we use contours, color maps, and height fields. In 3D, we use isosurfaces, volume rendering, and cutting planes. These techniques are essential in fields like medicine, engineering, and geoscience. Tools like MATLAB and ParaView simplify the task of analyzing complex data visually. Thank you so much for your time and attention. I hope this presentation helped you understand the concept and importance of 2D and 3D scalar field visualization.